Now, here's this last thing is this vocabulary word called enthalpy change. Enthalpy change is denoted by the letter H. Once again, it also tells us if energy is being absorbed or released by a system. It's usually measured in kJ or joules. And you know 1 kilojoules is equal to 1,000 joules. Okay, so that J stands for joules. Okay. So if something is endothermic, and you got to think about like now, let's think about chemical reactions. The energy that you're starting with, right? So your reactants, this is what you're starting with, is low. You have like a certain amount of energy. Now, if it's endothermic, right? This endothermic word here means that heat is entering, right? You are gaining heat, and heat is energy. So that means where you end up has to be a lot higher energy. So this is where your products is. This is where you end up. Now, you would think that it's like a straight line across, but in chemistry, there's actually like this weird little hump that needs to be drawn like this. It actually like pushes way up higher than you actually need so that it can like fall down into the right spot. So same thing here on the opposite side. If something is exothermic, right? You know, heat is what? You are losing heat. Remember, heat is just a type of energy. So if you're starting with a type of energy, so here we're starting with a certain amount, right? Reactants, R for reactants, this is where we're starting. Then P, products, you would end up losing energy, right? You end up with less energy. So remember, it's not a straight line. You have to like go up and then come back down. So you have to like jump up to like lose that energy. So it's all about, so don't really focus on where exactly the humps are. Think about where you're starting and your end point. Am I gaining energy or am I losing energy? Okay, so think about it that way. All right, so let's do like a quick summary of all our vocabulary words. So endothermic, energy is being absorbed. You know that. Q is heat and H is enthalpy. Anytime something is endothermic, we denote it with a positive value. So endothermic is definitely absorbed. You see a positive number. So Q is heat, H is enthalpy. So anytime you're trying to break bonds, you need to absorb energy. You need to like muster up all that energy to like break bonds so that you can form new ones, right? So breaking bonds does require you to gain and absorb a lot of energy. If you were to write this in a chemical reaction, the energy will show up in the reactants, which is before the arrow. This means you need that energy before you can actually make anything. So like, for example, here, it tells us that delta H, so enthalpy here, is a positive 32, right? So that means that every time you see that positive, you know you're gaining, absorbing energy. Now, you need this energy in order to start the reaction. So the energy has to be one of the ingredients, right? One of the reactants in order for this to work. So you always put it before the arrow. I usually put it at the very beginning as a sign to me to let me know that, hey, I need this energy or this reaction is not going to go, okay? Like this reaction cannot happen unless I have 92 kilojoules of energy, right? And that's why it's in the front. So then in the exact same fashion here, exothermic then, right? Energy then is being what? Released. How do you denote an exothermic reaction? Is by using a negative number, right? Negative, negative. Remember, Q is this heat, delta H is just enthalpy. You can write that in really quick. Now, after you like break bonds, so you like gain all this energy to break them, and then you form new ones, like you form little friendships and compounds, then when you form these bonds, you actually will release energy because you don't need it anymore. You're not like trying to break anything anymore. Now you're trying to be like nice and sharing, or like doing all that kinds of forming bonds, right? Forming friendships. So you can release energy, release that tension. Okay. Energy is going to appear in the product section, which is after the arrow, because now what you're trying to say is, I don't need this energy anymore. So now it can go away. We can exit out. I don't need it anymore. So when you look here, you can see that the energy is negative. So it's telling you, hey, we are losing energy. We're losing heat, right? Now, when you see it in a chemical reaction, you're not going to see it with a negative number. So here, we're going to see that if I just write energy here, right? This tells me if I see energy after the arrow, I'm losing energy. That's what it's saying. So if you look at this number really quick, this is where a lot of people mess up here, okay? You see that there's no negative here, but where is it located? It's located after the arrow, which means that, hey, I don't need this energy anymore, so it's actually going to go away. I'm going to like put it out into the surroundings because the system doesn't need it anymore. So you don't have to put the negative in a chemical reaction. In a chemical reaction, we always use plus signs, because plus signs doesn't mean like adding. It just means the word like and. Like, so like nitrogen plus hydrogen is going to make ammonia and lose 324 kilojoules. That's what that plus sign means in a reaction. It's just another word for like and. So the location of the number is what's actually more important, right, than anything. It's like, is it before or is it after the arrow? So if it's before the arrow, you know you need that energy in order for it to go. Okay, when it's after the arrow, you are throwing that energy away because you don't need it anymore. All right, and that's it.
Heat of reaction, or enthalpy of reaction, is the energy involved in a chemical reaction. We measure it in kJ, kilojoules. There's this fancy looking equation, delta H of reaction, so the change in enthalpy for the reaction is equal to, and then there's this thing, which is a capital Greek letter called sigma, and it means the sum. So it says the sum of all the heats for the products minus the sum of all the heats for the reactants. All that really means is you add up all the products, you add up all the reactants, and then you subtract total minus total. Okay, don't overthink it, even though there's this fancy Greek letter. It's not a big deal. It's really simple math, I promise. Don't freak out. Thermochemical equations are chemical equations that include the enthalpy change. So the coefficients represent the number of moles, and delta H of F is called the heat of formation. It tells us how much energy was absorbed or gained to make 1 mole of that compound. For example, liquid water has a heat of formation of negative 286 kilojoules per mole, which means that to make liquid water from hydrogen and oxygen, the elements have to release 286 kilojoules of heat. That's what that heat of formation means. Elements in their natural state, so an element by itself will have a heat of formation of 0 because it doesn't take any energy to be yourself. I'm going to give you a moment to write that. Okay. Let's look at the top of the next page. Here's that formula again. The heat of reaction is the sum of your heat of your products minus the sum of your heat of reactants. And again, the math here is, I promise, not very complicated. Here's what you do. For each reaction, use the heats of formation in the chart. I will always give you a chart. You don't have to memorize it. Use it in the chart to determine the heat for each reaction. Predict whether the reaction is endothermic or exothermic, and if energy is absorbed or released, write the thermochemical equation. Energy values in the equation should always be positive. Remember that exothermic means the energies in the products, endothermic means the energies in the reactants. This seems like a lot of information. We're going to do it, and you're going to be like, oh, this is really easy. So, our formula says we're going to take the products minus the reactants. So what we're going to do is, here's the reaction. We need to do the products, which are zinc and 2HCl. We need to add those up and then subtract the reactants, which are the ZnCl2 and the hydrogen. So we're going to plug in the numbers from the chart to do that. Now we have a little bit of a problem, which is that zinc by itself is not in the chart. But zinc is an element by itself. It'll have a heat of 0. So since it's an element by itself, for the Zn, zinc, we're going to just plug in 0. Then it says 2HCl, so I'm going to add 2 times HCl, and I have to go in this chart, and I have to find the number for HCl, which is negative 167.16. That'll add up my products. Then I have to separately subtract the sum of my reactants. So for ZnCl2, I go to the chart. It says negative 415.1, and then I have to add hydrogen. Hydrogen, H2, also not in the chart, but this is an element by itself. The only element here is H, and when it's an element by itself, its heat will be 0. So for the hydrogen, I'm using 0, and for the zinc, I'm using 0, because those are elements by themselves. So now I can simplify what's in these parentheses. Basically, 0 plus is obviously not going to change anything. So I do 2 times negative 167.16, and that's negative 334.32. Then I'm subtracting. Adding the 0 here, again, not going to change anything, so this is just negative 415.1. When you type this in your calculator, be careful that you don't miss one of the negatives. If you skip one of the negatives in your calculator, you're not going to get the right answer. Negative 334.32 minus negative 415.1 comes out to 80.78. And we're going to be using units of kilojoules for this. So that was step 1. We just added and subtracted. Step 2 says predict whether it's endothermic or exothermic, and if energy is absorbed or released. This was a positive answer that we got here. So when it's positive, we just learned on this page, when it's positive, it's going to be endothermic and energy is absorbed. So for step 2, I say it's positive, so it's endothermic. And I say, since it's endothermic, energy is absorbed. See, easy, not so bad. For number 3, write the thermochemical equation. Energy values in the equation should always be positive. Remember, if it's exothermic, energy is a product. If it's endothermic, energy is a reactant. So, this one was endothermic. Energy should be a reactant. So I'm going to take this amount of energy and I'm going to make it a reactant, 80.78 kilojoules. It's going to be on the reactant side of my arrow with the other reactants, ZnCl2 plus H2, and then the products will be on the product side, Zn plus 2HCl. Really, all you do is you copy this exactly in here. Just copy what they typed for you exactly in here, and then if it was endothermic, you put the heat on the reactant side, added, positive, If it were exothermic, we would put the heat on the product side added positive. And I'll do an example of an exothermic with you right now. Calcium carbonate reacts with hydrochloric acid to form calcium chloride, liquid water, and carbon dioxide. So we are supposed to do products minus reactants. So the products here are CaCl2, H2O, CO2, and it's minus the reactants, which were CaCO3 and 2HCl. So if I go plug stuff in for that, the CaCl2 in my chart is negative 877.3. That's got to be plus water, which in my chart is negative 286, which is plus CO2, which in my chart is negative 393.51. I am running out of room. I should have written smaller. And that's minus the reactants, which were CaCO3, which in my chart is negative 1207. And that reactant is plus the other reactant, 2HCl. So it's got to be 2 times the number for HCl in the chart, which is negative 167.16. I'm sorry, I ran out of room. I'm writing all sideways here. Again, since this says 2HCl, you do have to multiply the number from the chart for HCl times 2. So we can simplify everything in these parentheses. The first set, I'm going to add negative 877.3 plus negative 286 plus negative 393.15, or excuse me, 0.51, that's important. Make sure you hit all the negatives in your calculator. Again, if you skip a negative in your calculator, it's going to get you the wrong answer. And then over here, negative 1207 plus 2 times negative 167.16 is negative 1541.32. And then to get my final answer, negative 1556.81 minus negative 1541.32. Overall, that comes out to negative 15.49, and again, our units are going to be kilojoules kJ. So for step 1, every time I add up all the products, I separately add up all the reactants using the chart. And then once I have the total products and the total reactants, I just subtract products minus reactants to get this number. For step 2, we're just saying endo or exo, absorbed or released. We got a negative number here. And when we get a negative number, that means we're looking at an exothermic reaction and energy is released. So for step 2, I can just write exothermic, comma, released. For step 3, we need to write the thermochemical equation, where I write the reaction they gave me, and I have to add the heat into the reaction somewhere. So first, just copy the reaction, like straight down, exactly how they typed it. Just copy exactly what they typed. Then, after you have copied exactly what they typed into this line, you're going to take this number and decide if it goes on the reactant side or on the product side. When it's exothermic, we wrote down it goes on the product side. So I'm going to take that number and I'm going to write it on the product side. And it has to, when you put it in the equation, it has to be positive. So I know it was negative when I calculated it, but that negative just tells me it goes on the product side. When it's on the product side, it's going to be positive. Heating and cooling curves show energy changes. All matter follows the curve when energy is added or lost. Horizontal portions of the curve indicate a physical state change. So the temperature remains constant when it's horizontal, right? If your temperature is on your y-axis, which it is, and there's a flat line, that means the y coordinates are not changing. There is a change in particle position, resulting in a change in potential energy. They're changing position, that's a change in potential energy. Slope portions show a temperature change, which indicates a change in the thermal energy, or the heat energy, or the enthalpy as well. So we gotta label this heating curve for water, where at part A, and you may remember this from like unit 1, yes, we're doing this again. If this is water, we've got 0 degrees Celsius here and 100 degrees Celsius here. It is, when we go this direction, we've got melting. Or, whoop, nope, sorry, that's wrong. This is the spot where it's solid, and then on this direction, it's melting, and this direction, it's freezing. Here, water is liquid, and if we go this direction, we've got vaporization. And if we go back the other direction, then we've got condensation. And up here, it's a gas. Notice that when it's melting and freezing, it's 0 degrees the whole time. When it's vaporizing and condensing, it's 100 degrees the whole time. So down here, we have the lowest energy. And up here, where it's a gas, we have the highest energy.